Okay, so this is a walkthrough of the quiz Are You Ready for Exam 2? And we'll be going through each of the questions, explaining some of the considerations for which answer is the correct one, and a general strategy for, working with this kind of material. The first question gives you a data table taken at different temperatures. Looks like time in hours, and the concentration of a substance called PCA. And so there's three different temperatures, and the question asks, what is the rate order? So the general strategy here is to So the general strategy is to take the time and create three different columns, right? Because what we need to do is we need to calculate the rate constant given which function is linear. And so we want to know, is it zero order, is it first order, is it second order? If it's going to be linear, that means that what we're going to be able to do is take a look at the change in concentration with respect to time. And so we're just looking at the 97.3 degrees, which will be the same for each of the temperatures, right? The rate order is not going to be dependent on the temperature. We write down the first three values, time 0 to 8, and then we're going to make corresponding values of the logarithm. So we can evaluate first order behavior, and we're going to do the reciprocal, which is going to evaluate second order behavior. So this sets up the problem to know that we have zero order, first order, or second order. The next thing we're going to do is calculate the rate constant going from 0 to 2 and the rate constant going from 2 to 8. When we see the same value that occurring between two different time intervals, then we'll know that that's the order in question. So let's take a look. We do this for the concentration, and we do that for the ln. So the ln of 17 minus L of 15.31 divided by 2. And we do the same thing for the time point 8. And then we do it also for the reciprocal plot, right? So we're calculating K for all three, right? And we make a table. And what we see is when we evaluate the 0 to 2 and 2 to 8 for the concentration and the 1 over. So we're going to evaluate all three of them. And when we do that, we see that we get 0.84 and 0.6. So for the concentration versus time, which is zero order kinetics, we see that this data set does not represent zero order kinetics. We do the same thing with the ln, and we see we get the exact same value for K, independent of whether we take the time point 0 to 2 or 2 to 8. And then when we do the first order, second order analysis, we see that it's not the same. So the best choice is that the ln of the concentration is linear. You have the same rate constant showing a linear performance independent of the time interval. And that would lead us to conclude first order kinetics. Okay, so the second question is about calculating the rate constant at 97.3 degrees Celsius. We just did that in a way because we needed to know, was it zero, first, or second order. So to do that, we calculated the rate constant. So we know it's first order. That means that minus K is going to be equal to the difference in the ln of two concentrations divided by the time interval. It doesn't matter what time interval we pick. We just happen to pick the first one. If you do that, minus 0.523 as we did in the other problem. And it's going to be units of hours, and we see that that answer is C. Okay. So let's go to 3. Question 3 asks if the rate of the reaction, to determine or estimate the rate of reaction at 91.3 degrees when the concentration is 9 times 10 to the minus 8 molar. All right, so one of the things we need to do is recognize that the reaction rate is equal, since it's first order, is equal to K times the concentration 1 to the first power. So we need to know K at 91.3. Right, so we can just plug in the concentration. Well, the K at 91.3, we're going to use the same strategy. The ln of 17, we'll use the data point, the first two set, 15.76. We do that, and we see that we're going to get K to be 0.379, which we can plug in for the rate. And now we see we get an answer, 3 times 10 to the minus 4 molar per hour. That gives us B. So question number 4 asks, okay, well, at a different temperature, what would be the half-life? Right, so we did this in class where we took a look at, if we have first order kinetics, we have the integrated rate law here, which we should be able to find the half-life because we make the substitution for concentration that it's C0 divided by 2. And we find out that the time when we bring the ln of C0 over to the left-hand side and subtract and divide, as we did in class, we can solve for K this way, and we see that the ln of 1/2 and the concentrations cancel, divided by minus K. So at 85.3 degrees Celsius, we need to find out what K is. This is going to be different for each of the temperatures. And so we do the same thing. We take the delta of the ln, divide by the time interval. Again, we could pick any of the time intervals because we expect this to be linear, since we've already demonstrated first order behavior. And we get minus K to be minus 0.027, which we can now calculate the half-life, and we get 25.4 hours, which is one of the options. Okay. So question number 6, we'll come back to 5. It's just there's a slight problem with ordering. So question 5, we have a mechanism, and the question is, what's the rate law given this mechanism? So we have to write the preliminary rate law, which is step 1 for step 1 and step 2. We see that the preliminary rate law for step 1 is K1 times the concentration of PCA and H3O+. This is an aqueous solution, right? These are ions with other solution with other species. And in step 2, we see the rate 2 is K2 times HPCA+. And of course, water does not appear in the rate for step 2, the step in the rate 2, because water has the concentration of water is considered a constant, so it's just included in the constant K2. So we have a fast-slow mechanism, which means that the HPCA is unacceptable because it's an intermediate. So what we have to do is we have to substitute out using the fast equilibrium that occurs in step 1. When we do that, we put the products in the numerator, PCH3+ in the denominator. And now we have a straightforward way in which to solve for HPCA. So if we do that, we see that we have the equilibrium constant times H3O+ times PCA. We can now substitute this into what is the step 2, the preliminary rate law, and we then recover the overall rate law, which is K2, Kc, H3O plus PCA, which we can combine K2 and Kc into a constant K, and we get H3O plus times PCA. That's the rate law. And that would be the answer. Okay. So let's go back to 5. So we skipped 5. Let's go back to it. So here we have the rate. We have the ratio of the rate constants is 1.9 times faster at one temperature than something else, and then at another temperature, lower temperature. So if K2 is 1.9 times K1, then we can make, and we know T2 is 97.3, T1 is 85.3. What we can do now is we can use one of the two forms that's most convenient to us. So we have K2, K1 is minus E delta ER over T2 over T1, right? That's one form, and that's very convenient when you already have the activation energy. There's another form in which we have the ln of K2 over K1, which is E to the minus delta E over R. And this form is much more convenient when you have the K1 and K2, T1 and T2, and you're solving for delta E. Much more convenient because now the activation energy is not in the exponent. They're both equivalent. All we did was take the ln of both sides, right? And so we'll use that one. We know the ratio is 1.9, so we can just plug that in there. We don't know the activation energy, but we know R. We can just plug in the temperatures, making sure that we put in the specific Kelvin temperatures. We plug that in. We can then solve for delta E because the ln of 1.9 is 0.64. Multiply by R, 8.314. Divide by the result of the reciprocal of 370 minus the reciprocal of 358. And when you do that, you get about 59,000, which was 60 kilojoules per mole. Answer is A. All right, so question number 7 was, and the rest of the problems are going to be an analysis of this mechanism. So what role does H3O plus have in this reaction? Well, let's take a look. So it starts as a reactant and ends as a product in step 3. So it starts as a reactant in step 1, ends as a product as step 3. That means that when you add up all the steps, which gives you the overall reaction, it's not present because it cancels on both sides of the reaction. In that case, we call that a catalyst, right? That lowers the activation energy. It maintains the potential energy of the reactants and overall products. It doesn't change the equilibrium constant, but it does change the rate. By lowering the activation energy, increases the rate. So it's a catalyst. And to be complete, we could see that HPCA is something by comparison starts as a product in step 1, ends as a reactant in step 2. That's characteristic of an intermediate. That cannot be in the rate law. So a catalyst can and an intermediate cannot. So we would put not in the rate law, overall rate law, and catalyst can be in the rate law. Okay. So let's take a look at some of the extra questions. Once we find the rate law, we're going to say find the rate versus H3O plus for the reaction. So we had the rate law. It's here. K times PCA times H3O plus. H3O plus is shown to the first power. So if we were going to look at the rate of the chemical reaction versus the concentration of H3O plus, we would see a straight line with the slope being K PCA, which we would assume that PCA concentration is constant during this change. Okay. All right. So the next question was, given that rate law, what is the concentration of H3O plus as a function of time? Right. So we have first order kinetics. Right, first order, so we put time here, concentration of H3O plus. Here's our rate law, H3O plus to the first order, PCA, and we would know that we would start at some point at time 0, and then we would see exponential decay of H3O plus since it's first order. All right, so the next question, additional question was during the energy diagram. So let's do the energy diagram, potential energy versus reaction rate. So we can see for the, so here we have a fast step, which is, difficult to anticipate. We don't really have AA bonds or AB bonds, so we're just going to put them equal. The main thing is that we should show that step 2 is exothermic because we have two particles making one, this particle C. And so in the slow step, we should have an exothermic. We should also have a high activation energy for step 2. compared to step 1, right? Okay. So let's go into the deeper analysis into step 2. So step 2 has, we can look at it and say, what is the sign of delta H and delta S for step 2, right? That would help. And then if you have delta H and delta S, write out the E versus S curve, the delta G versus T curve, and the K versus T curve, right? So it's a very nice analysis of Unit 5 modules 1 and 2 for a chemical reaction where it's pretty clear what the signs of delta H and delta S are. So by looking at this, we see that two particles are making one. From an energetic argument, we know that bonds are being formed. That wasn't present before. So delta H is going to be less than 0, and delta S is going to be less than 0 also. This is probably the clearest analysis for the signs of delta H and delta S, two particles going into one. All right, so the E versus S curve here, we would show that the reactants would be higher potential energy than the products, and that the reactants have higher entropy than the products. So we see that the R would be in the top right corner, P would be in the bottom left. This would definitely show some type of delta H and delta S have the same sign, so we know there's going to be a critical temperature at which directionality will change. We can show that in a delta G curve, so we put the reactant favored when delta G is positive, product favored when delta G is negative. We start off with the sign of delta H when temperature equals 0. It's down there at product favored. The slope of the line is minus delta S. Delta S is negative, so the slope has to be positive. We see it crossing the axes at delta G equals 0. The K versus T curve, we draw our critical value of 1. We should see also a critical change in the equilibrium. We see that the reactant favored when K is less than 1, product favored when K is greater than 1. And so we all see the same story here, that exothermic favors products, the change in entropy favors reactants. And so based on that, we see the change in both the potential energy favoring the products at low temperatures, reactants at high temperatures. That's consistent with our E versus S curve, our delta G versus T curve, and our K versus T curve. All right. So these are all the concepts that from the Chemical Thinking Chemistry 152, Unit 5, Module 1 that you're responsible for. This should be fairly straightforward, and if you have any questions, you should definitely ask either in the tutor room, SI instructors, or come to office hours.